Hello everyone! Today, let's talk about BIERv6. BIERv6 is a new multicast technology that encapsulates into packet headers a set of nodes to which multicast packets are destined as a bit string. BIERv6 does not need to explicitly establish multicast distribution trees, nor does it require transit nodes to maintain per-flow states. This means that BIERv6 can be seamlessly integrated into SRv6 networks, reducing protocol complexity. MVPN over BIERv6 uses BIERv6 as a bearer tunnel, encapsulates VPN IP multicast traffic using BIERv6, and transmits the traffic over a VPN in multicast mode. On the network shown in this figure, the sender PE needs to forward the multicast data received from CE1 to the receiver PEs in the same VPN instance as the sender PEs. Each receiver PE forwards the received multicast data to the connected CE, which then forwards the data to VPN users. BIERv6 uses unicast routes to forward traffic. Therefore, to ensure that the unicast VPN runs properly, Layer 3 VPNv4 over SRv6 or EVPN Layer 3 VPNv4 over SRv6 must be configured in advance of MVPNv4 over BIERv6. In this course, we will not go into details to describe this configuration. Between the MVPNv4 over BIERv6 network and VPNs, IGMP and PIM are used to allow VPN users to join or leave multicast groups. The IGMP and PIM configuration in this scenario is similar to that in common multicast scenarios. BIERv6 extends the IGP and BGP. On an MVPNv4 over BIER6 network, is used to generate a bit index forwarding table, or BIFT for short. BGP is used to transmit routes, so that tunnels are established, and multicast users join multicast groups. The configuration roadmap involves 3 steps. First, configure basic BIERv6 functions and enable is v6 for BIERv6 so that a forwarding table can be generated in the BIERv6 control plane. Second, establish BGP MVPN peer relationships to transmit multicast routes. Third, configure a tunnel to carry multicast traffic. The tunnels established between PEs to transmit C multicast data over the public network are called PMSI tunnels, which are further classified into IPMSI tunnels and SPMSI tunnels. An IPMSI tunnel connects all PEs in the same MVPN and is used to forward data by default. An SPMSI tunnel connects only some PEs in the same MVPN and is used to transmit VPN data only to the PEs that require the data. One or more SPMSI tunnels can be automatically generated based on the SG information of different multicast services. Here, we will use an IPMSI tunnel to carry multicast traffic as an example. Let's get started with the configuration. First, configure IPv6 addresses for interfaces and enable is. Next, we need to configure basic BIERv6 functions. 1. Run the subdomain command to configure a BIERv6 subdomain ID for the current node. Note that the ingress and egress of multicast traffic must be in the same subdomain. 2. Run the BFR prefix command to configure a BFR prefix for each BFR. Note that a BFR prefix is used to flood BIERTLV information and must be the address of each BFR's is v6-capable loopback interface. 3. Run the protocol is command to set is as the underlay protocol for advertising BIERv6 packets. 4. Run the endBIERlocator command to configure an endBIERSID for each BFR. The endBIERSID can be flooded to other BFRs. When forwarding a BIERv6 packet, a device sets the destination address in the packet header to the end beer SID of the next hop. 5. Run the encapsulation type command to set the encapsulation type, BSL, and max SI for BIERv6 packets. BSL indicates the bitstring length. Devices in the subdomain must be configured with the same BSL. Max SI indicates the maximum set ID in the subdomain. Set ID is equal to the integer of BRFID minus 1 divided by BSL. After completing the basic configuration of BIERv6, enable is and beer so that each node in the BIERv6 subdomain floods its BFR prefix, subdomain ID, BFR ID, BSL, and path calculation algorithm information through v6 for BIERv6. Each node contains the BFR neighbor to each BFER through path calculation and generates BIFT entries that contain bitstring information. Here, node P is used as an example. After receiving BIERv6 information flooded by other nodes, node P generates 2 BIFT entries, each with one BFR neighbor. The BFR neighbor to the node with BFR ID 2 is PE2, and the BFR neighbor to the node with BFR ID 3 is PE3. In addition to the unicast peer relationships that have been established between PE1 and PE2, and between PE1 and PE3, establish BGP MVPN peer relationships between PE1 and PE2, and between PE1 and PE3. After the configuration is complete, run the display BGP MVPN peer command on P1. The command output shows that the BGP MVPN peer relationships have been established. Through the BGP MVPN peer relationships, PE1, PE2, and PE3 can transmit multicast routes. Finally, configure the PEs in the same VPN instance to use BIERv6 tunnels to carry multicast traffic. PE1 is used as an example here. 1. Run the multicast MVPN IPv6 underlay command to configure an MVPN IPv6 ID for use as the originating router's IP address in the AD routes to be sent. You are advised to set this ID to the IP address of a loopback interface. 2. Run the multicast routing enable command in the VPN instance IPv4 address family view to enable the multicast function. Only after the multicast function is enabled in the VPN instance can other multicast-related commands be run in this instance. 3. Run the IPv6 underlay enable command in the MVPN view to configure the device to use IPv6 tunnels to forward IPv6 packets. Only after this command is run can AD routes be exchanged between PE1 and PE2, and between PE1 and PE3 in BIERv6 scenarios. 4. Run the sender enable command to configure the current PE as a sender PE. 5. Run the source DT4 locator command to configure a source DT4 SID for use as the source address in the IPv6 header, and for the receiver PEs to differentiate MVPN instances. 6. Run the beer command in the IPMSI view to set the tunnel type to beer. Because the device has been configured to use IPv6 tunnels to forward IPv6 packets, the IPMSI tunnel type is BIERv6. The sender PE function, source DT4 SID, and IPMSI tunnel type do not need to be configured on receiver PEs, which are PE2 and PE3. However, you need to run the C multicast signaling BGP command on PE2 and PE3 to configure them to use BGP as the signaling protocol to transmit C multicast routes to the sender PE. After the configuration is complete, run this command to check IPMSI tunnel information of VPNA. From the command output, we can find that the tunnel type is BIERv6. and that the source DT4 SID, subdomain ID, and the BFR prefix are what we have configured. In addition, an IPMSI tunnel has been established, with PE1 as the root node and PE2 and PE3 as leaf nodes. This means that MVPNv4 over BIERv6 configuration is complete. Now, let's talk about the route transmission and data forwarding on an MVPNv4 over BIERv6 network. Let's begin with route transmission. After establishing BGP MVPN peer relationships with PE2 and PE3, PE1 sends intra-AS IPMSI AD routes to them. The routes carry information about the RT, next hop address, RD, and items that we have just configured, including the PMSI tunnel attribute, source DT4 SID, and the originating router's IP address. After receiving the routes PE2 and PE3, reply with leaf AD routes, which also carry the configured PMSI tunnel attribute and the originating router's IP address. Of these, the PMSI tunnel attribute includes the subdomain ID, BFR ID, and BFR prefix. Based on the received routes, PE1 calculates the set ID and bit string to be encapsulated into the BIERv6 packet header. In this way, multicast forwarding paths are established between the sender PE and receiver PEs. In addition, as PIM is enabled on the interfaces connecting the MVPNv4 over BIERv6 network to VPNs, receiver PEs can construct C multicast routes based on the PIM join prune messages received from the VPNs and send the C multicast routes to the sender PE. After receiving the C multicast routes, the sender PE converts them into PIM join prune messages and sends the messages corresponding to the VPN CE. C multicast users then join or leave multicast groups. Next, let's talk about the packet forwarding process. 1. After receiving a C multicast packet, PE1 selects a PMSI tunnel based on the source and destination addresses of the packet, inserts the outer BIERv6 packet header with the bit string of 0110, and sets its source DT4 SID as the outer source IPv6 address. 2. PE1 queries its BIFT and finds that the next hop is the P. Therefore, PE1 sets the destination address of the multicast packet to the end BIER SID of the P and forwards the multicast packet to the P. 3. After receiving the packet, the P queries its BIFT and finds that the PE2 is the next hop to the node whose BFR ID is 2, and that PE3 is the next hop to the node whose BFR ID is 3. Then, the P sets the destination address to the end BIER SID of PE2 before sending the packet to PE2, and sets the destination address to the end BIER SID of PE3 before sending the packet to PE3. 4. After receiving the multicast packet, PE2 and PE3 determine that they are the destination nodes of the packet according to the corresponding bit string. Remove the BIERv6 header, and then forward the packet out of the MVPN over BIERv6 network and into the corresponding VPN for forwarding. To sum up, BIERv6 extends the IGP and BGP, generates BIFT entries based on information flooded through the IGP, and transmits BGP MVPN routes to establish tunnels and allow multicast users to join or leave multicast groups. Unlike traditional multicast protocols, BIERv6 does not need to create MDTs, reducing protocol overhead. With this, we wrap up this configuration case of MVPNv4 over BIERv6. Thank you for watching.